Welcome to a new video about control realization. This is our example number 7. In this example, we will discuss the realization of a lead controller using active components. So we will do it step by step in order to get the specific circuit and also its component values. And of course, for that, we will work out the calculation step by step and also verify these in our SPICE simulations. So let's look at our circuit and also the required transfer function. This is the transfer function of the lead controller, and we would like to design a physical electric circuit for this transfer function. There are many options, and we will just show you one of the options here. So the solutions, I start first with a diagram in order to illustrate the concept here for this lead controller. This lead controller has already some gain in the DC and also gain at very high frequencies, and that is determined by looking at the value of S. If S is exactly 0, that means DC, then you have 64 times 0.5 over 8, and together it will produce 4, so we will have some gain at DC. And if the S is approaching infinity, that means we have a ratio of 1 here for this part, and you get a 64 as a gain. That means this lead controller will definitely require some additional gain. It is not just a lead controller by a pole and a 0. So we can now divide the problem in two sections. One of them is just a lead controller, which provides this pole and the 0 in the pole. And we have a gain stage here. And then in cascade, you can make this lead controller completely as given here. So we can now say in each section, we will determine the transfer function and from there also the specific circuit. Now the lead controller transfer function can be realized by this circuit, specifically the R1 parallel with the capacitor and also the R2 here. So that's from the input. And the cascade will be then the gain stage, in this case a non-inverting configuration using the operational amplifier. So we can now determine the G lead and the K and then cascade them together to get this complete circuit as shown here. So the transfer function of the circuit given here can be then written like the K times G lead. K is just the transfer function of the non-inverting amplifier. This is quite standard and familiar. And that formula is 1 plus the feedback resistor divided by the resistor here going from the inverting node to ground. That's shown here. The G lead transfer function is shown here, and you can recognize here very easily the 0 and the pole expressions. Together, you will have now the product of the K and the G lead, which is shown here. And this must be compared to the controller transfer function GC later. So we have the circuit transfer function and the transfer function of the controller. Okay, moving on, we'll see now the transfer function again, but now with some colors to designate the poles and the zeros and also the gain more easily. This is the circuit we have chosen, and this part is as said before the specific lead part, and the second part is our gain stage K. And now we can say by comparing the terms of the H and the G of C, we see the following. 0.5 here, the 0 must be this red, so 1 over R1C. And the 8 will be the blue one, is this expression. And the pink one here is then 64. So we have now 3 equations. But we have 5 unknowns because we have RF, RM, R1, R2 and C. So we need to select 2 of the 5 unknowns. So that means selection of, for example, the capacitor is a practical one. So we say take the capacitor, and I just select here a convenient value of 100 microfarads. Now when you do that, you can now calculate using this formula the value of R1 using here the expression. They will give you for this R1 using this capacitor 20 kilo ohms. Now once you have that, you can now write down this second equation as shown here, and this 1 over R1C is actually 0.5. That's actually shown here in red. So you go down, and that will make then 1 over R2C 7.5. Since C is known, we have selected that as 100 microfarad. We can calculate R2 as shown here, and that will give you 1.333 kilo ohms approximately. So the resistors are now calculated for the lead controller. Now the next one is the calculation of the RF and RM. Again, as said, we need to select 2 of the 5 unknowns. We already selected one, so the other one is what we need to select for the gain stage. Now we can take, for example, Rm as 1 kilo ohms. That will then make the Rf this expression, which is then 64 minus 1 times the Rm. That's just the rewriting of this expression. Now, since we know that this is down 10 to the power 3, 1 kilo ohms for the Rm, that will give you 63 kilo ohms together. So we have now everything for this lead controller with the gain. Okay, and the circuit here by this SPICE circuit is now shown here. You can see the R1, C, R2, the RF, and also the RM here, and also the operational amplifier, which is given here in ideal configuration. Okay, now looking at the solutions further, and we would like to now look at the simulation results. This simulation results show you the low frequency gain. You see here the low frequency gain, which is 12.04 dBs, which is 4 as said before, because when you go to the transfer function of the controller, substitute there here 0, you will get exactly 4 as a scalar. And if you do 20 log of that value, you get 12.04 dB approximately. So this is verified. Now let's also look at the other extreme, which is the high frequency gain. It says 36.12 dB in this Bode plot, which is 64. And why is 64? Because if you look at the infinite value, it will be the ratio here is 1. So you'll get 64, and when you do again the calculations using a 20 log formula, you get 36.12 dBs. So that's also verified. The two other things we need to verify is the lead 0 and the lead pole. The lead 0 is shown here. It is determined by looking at the low frequency gain and going up by 3.01 dB. That's what we did here. And the frequency there is in hertz, 79.88 millihertz. When you convert that to radians per second, you need to multiply this by 2 pi. That will give you approximately 0.5 radians per second, which is a nice result as we need here, because it's also 0.5 for the 0. Now going to the pole is determined by looking at the high frequency gain and then going down by 3.01 dB as said. So this is 36.12. Going down you go to 33.11 dB. That happens at 1.268 hertz. Again, multiplied by 2 pi, you will get 7.967 radians, which is very close to 8 as required here. So you see the calculations do match very well with the simulations, and if you of course take into account some rounding off errors, this is almost exact. Alright guys, this is our example about the lead controller using the active circuit realization. We have seen that the simulation results confirm our calculation, also the circuit realization very nicely. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video about the active realization of a lag controller.